Prime numbers have a property that if it divides the product of two numbers, then it divides at least one of the two terms in the product. So the motivation to define prime ideal comes from the prime numbers. Also, prime ideals and maximal ideals help us to determine whether a quotient ring is a field or an integral domain. While defining a prime ideal or a maximal ideal, we talk about a proper ideal of a ring. So, a proper ideal of a commutative ring R is said to be a prime ideal if the product of two elements belong to the ideal implies either of the two elements belong to the ideal. That means if the product AB belongs to the ideal A, it implies either A belongs to A or B belongs to A. Now, a maximal ideal, a proper ideal of a ring R is said to be a maximal ideal if whenever B is an ideal of R and A is contained in B is contained in R, then B equals to A or B equals to R. So this means that if A is a maximal ideal of the ring, then there cannot exist any other ideal that is contained between A and R. Now we do two criteria that help in determining when is a quotient ring an integral domain and when it is a field. These two criteria are important as usually one of them is asked in exams. So the first one says that if R is a commutative ring with unity and A is an ideal of R, then R quotient A is an integral domain if and only if A is prime. Okay, so let's do the proof. The proof is quite simple. So we assume that R quotient A is an integral domain and we have to prove A is prime, right? So now we let two elements A and B belong to R, the ring, and the product AB belongs to the ideal A. We have to show that either A belongs to A or B belongs to A. So because AB belongs to A, by the theory of cosets, we get AB plus A is equal to A, right? By the property of cosets. So this means that A plus A, B plus A, this is equal to A, right? Because of the way we have defined the multiplication. So here A is the zero element of the quotient ring R by A. Okay, so because R by A was an integral domain and the product of two terms equals to 0, so this implies that either of the terms is equal to 0. So either A plus A is equals to 0, that is the zero element of R by A, which is A, or B plus A equals to A. Why? Because A is the zero element of R quotient A, right? This implies A belongs to A or B belongs to A, which was what we had to prove, and hence this implies A is a prime ideal. Now let's look at the converse. Now we assume that A is a prime ideal. Now we have to prove R by A is an integral domain. Okay, so proving an integral domain means that we have to show it is a commutative ring with unity and it has no zero divisors. So clearly R quotient A is a ring. We had proved it in our previous video, and since R is a commutative ring with unity, so if 1 is the unity of R, then 1 plus A is the unity of R quotient A. Also because R is commutative, so we let A plus A belongs to R quotient A and B plus A belongs to R quotient A. So A plus A into B plus A. This would be AB plus A, and because R is commutative, so this is equals to BA plus A, and this is equals to B plus A into A plus A. Hence our quotient A is commutative. Now we have to prove it has no zero divisors. So we suppose that, so we let A plus A into B plus A equals to 0 plus A. This is the zero element of our quotient A, which is equal to A. Okay, so this implies AB plus A is equals to A, and this implies that AB belongs to A. Now because A was what? A was a prime ideal, so it means that either A belongs to A or B belongs to A by the definition of prime ideal. So this means that either A plus A equals to A or B plus A equals to A. Now this is what? This is the zero of the quotient ring R by A, and hence if the product of two terms is 0 in R by A, one of them is 0, and hence we get R quotient A has no zero divisors, and so it is an integral domain. Let's see the next criteria now. This criteria says that if R is a commutative ring with unity and A is an ideal of R, then R quotient A is a field if and only if A is maximal. So the proof. So we do the forward part. First we assume that R quotient A is a field. We'll prove that A is maximal. So we assume that there exists an ideal B of R such that B is contained between A and R. So if B is equals to A, we are done. We don't have to prove anything. Then A would be maximal, right? So otherwise, if B properly contains A, we will show that B equals to R. Okay. So clearly B is contained in R. Now we have to show that R is contained in B. So because A is properly contained in B, इसका मतलब क्या है कि B का एक ऐसा एलिमेंट है जो A में नहीं है. So we let small b be the element in B which is not in A. That is, B belongs to B, but B does not belong to A. Okay, so because B does not belong to A means that B plus A is not equal to A, right? And A is the zero element of R by A. So B plus A is not the zero element of R by A, right? So because R by A is a field and this is a non-zero element, so it is a unit. That means it has an inverse. So we let C plus A be the inverse of B plus A. That is, there exists C plus A in R quotient A such that B plus A into C plus A is equals to 1 plus A, the unity element in R quotient A. So because now B belongs to B and C belongs to R and B is an ideal, so BC belongs to B, right? Because B is an ideal. Now 1 plus A is equals to B plus A into C plus A. So this is equal to BC plus A, which implies that 1 minus BC belongs to A, right? Now this A is contained in B, properly contained in B. So 1 minus BC plus BC, this is equal to 1. So 1 belongs to B because 1 minus BC belongs to B and BC belongs to B. from here BC belongs to B, and from here 1 minus BC belongs to B. So this implies that 1 belongs to B. The unity element of R belongs to B, and we have a result that if the unity element of a ring belongs to an ideal, that ideal is equal to the ring. So this result implies that B is equals to R, and hence A is a maximal ideal in R. Let's see the converse. We now assume that A is a maximal ideal in R. We will show that R quotient A is a field. So first of all, note that because R is commutative implies R quotient A is commutative. This is similar to the proof that we did in the criteria for R quotient A to be an integral domain. Also, because R contains a unity, say 1 is the unity of R. So 1 plus A is the unity of R quotient A. Now we only have to prove that every non-zero element of R quotient A is a unit. So we let B plus A be a non-zero element. The zero element of R quotient A is the ideal A. So non-zero element means that it is not equal to A. So this implies that B does not belong to A by the property of cosets, right? So we shall show that B plus A is a unit, that is, it has a multiplicative inverse. So we consider a set B. It consists of elements of the form BR plus A. Here R belongs to the ring R and A belongs to the ideal A. Now, because the elements in A can be written as B into 0 plus A, so this belongs to B. This is of the form BR plus A, so it belongs to B, which implies that A is contained in B. Also, because this element B, which is in B but not in A, so A is a proper subset of B, right? Now B is an ideal of R. This can be verified by the ideal test that we did in the previous video. So now A is properly contained in B, which is contained in R, and B is an ideal of R. Because A was a maximal ideal, so this implies that B should be equal to R. Because A is a maximal ideal, so there cannot be any ideal lying between R and A. So B should be equal to R, which implies that 1 should belong to B, because 1 is unity and unity belongs to R. So we let 1 equal to BC plus A dash. Okay, where A dash belongs to A. Now consider 1 plus A. This can be written as BC plus A dash plus A, which can be, because A dash belongs to A, so we can write it as BC plus A, because A dash would be absorbed by A. So this is equal to B plus A into C plus A. And hence C plus A is the multiplicative inverse of B plus A, which implies B plus A is a unit. And hence R quotient A is a field. This completes this criteria. So we conclude this video with these examples. These can be proved easily with the criteria that we have done previously. So the example of prime ideal comes from the ring of integers Z. So nz is a prime ideal of Z if and only if n is a prime. And the ideal generated by x squared plus 1 is a maximal ideal in Rx. This result can be proved by showing that Rx quotient x squared plus 1 is isomorphic to the ring of complex numbers. So because complex numbers is a field, and hence our quotient x squared plus 1 is a field, so x squared plus 1 is a maximal ideal.